I come up with 4.40. Yes? Okay. So now, that kind of helps us out with the first part. Now we're still also trying to figure out the concentration of our carbonate ion, correct? So that means that we have to dissociate our hydrogen carbonate, get that last hydrogen off of it. So we break it apart, and once again we're going to get our hydrogen ion plus carbonate. And then we're going to set up our ice table once again. And this time around, well, since we're starting with hydrogen carbonate on the left-hand side, we already know what its concentration is. That's a 3.99 times 10 to the negative fifth molar. Now, here we have initial concentration for one of our products. Okay, because we also had hydrogen ions from the first reaction, correct? So its initial concentration is also going to be 3.99 times 10 to the negative fifth molar. Carbonate, what are we going to put down there? 0, because we don't have anything at the beginning for carbonate. All right, now for our change in this situation, reactants, we're still going to have a negative X for the change. Why? No, that's what we do. But if we look over here, since with one of our products we have an initial concentration of 0, can we take anything away from 0? Answer is no. That's the reason why. Okay? Alright, so for the hydrogen ion and the carbonate ion, its change is going to be a positive X. Equilibrium, 3.99 times 10 to the negative fifth minus X. For the hydrogen ion, 3.99 times 10 to the negative fifth plus X, and for carbonate, it's X. Now we can put everything into our formula, but this time around, since we are in our second reaction, we use the second dissociation constant. All right? So 5.6 times 10 to the negative 11th is equal to 3.99 times 10 to the negative fifth plus X times X all over 3.99 times 10 to the negative fifth minus X. Okay, so dissociation constant, very small, right? So what can we do with that minus X?
It's out of here.
It's out of here. Now, guess what else we can do in this situation? We can get rid of that plus X as well. Because since the dissociation constant is so small, there's not going to be that much change. Okay? So if we get rid of that plus X, gone. What else can we do in this situation now? We can cancel everything out except for the X is equal to 5.6 times 10 to the negative 11. Does everybody see that? All right, so X is equal to 5.6 times 10 to the negative 11 molar. The only thing that we have X on at equilibrium is the carbonate ion. So that is our carbonate ion's concentration. Okay, now why didn't we have to find the pH in the second dissociation? Well, did anything really change with the hydrogen ion? No. Okay? Now, if the first dissociation constant was like times 10 to the negative second, times 10 to the negative third, there would be a huge change from the first to the second. Okay? But this one, we don't see it. Okay, questions, any kind of questions? All right, so like I said, I got a 5-prong assignment for you, dealing with weak acids and weak bases. We got 20 minutes left. Start working on it. Got any questions? I'm here.